Oh. Hmm. Hmm.
I think we should proceed. So good afternoon, everyone. My name is Marcin Kurpas. I come from University of Silesia, south of Poland. So as some of you may know, I already work in the field of spintronics, DFT calculations, which I started being a postdoc of Jarosław Fabian. So I hope the coffee has already woken us up after this nice lunch. And the first talk in the afternoon session will be given by Branislav Nikolic, and the title of the talk is Spin-orbit torque in van der Waals heterostructures of magnetic two-dimensional materials. One announcement before the start. So we have now three talks, and after Oleg Yazayev's talk, there will be a coffee break. 15 minutes, so because we have already 15 minutes delay, just please be strict. This is to the speakers. Try to be strict in time, that we don't land really at 6 here. Okay, so just some advertisement. I think this will be the first talk with real-time calculations, maybe, or drawings. So let's looking forward to your talk.
Okay, thanks for listening immediately after lunch. So it is a great pleasure to give this talk in front of this distinguished audience composed of famous researchers in different branches of spintronics. Also, it is a pleasure to be first time in Brazil. As I told some of you, when I was in graduate school in 1990s, I shared apartment with a bunch of Brazilians, and they would always say, you know, truth is much better in Brazil, and our music, maracatu, they were from Recife, is better than this music in US, and then the beach is much better. And I can say that everything they told me 20 years ago, and now we can confirm it experimentally, is true. In particular, we do have a beach. This is Delaware Beach, also Atlantic Ocean, but water is usually very cold, and there is always some big guy preventing you from jumping into the water because there are strong waves and, you know, very unfriendly to children and so on. But this morning, Igor, myself, and other people did really swim, and it was nice in the warm water of Natal. Okay, the most important piece of information on this first slide is actually this red link. On this red link, you will be able to find all the papers I mentioned in red ink, which are my own, so you don't have to do these proxies and all this stuff. And also some of our latest research has movies. So if you go to the journal website, most of the time they won't give you the movie, but you can get them from this website, and I will be running some movies in this talk as well. So the most important slide, people who have contributed to this, most of the stuff in this specific talk focused on 2D materials has been done by my current postdoc, Kapil Debdolui, as well as Marko Petrovic, and then collaboration with mathematics professor Petar Plehac, as well as with distinguished member of our audience, Jarosław Fabian, and his graduate student, Klaus Zollner. And then these are my former graduate students from US, and I also had a graduate student I supervised in Colombia. And then we do often collaborations in terms of grants and discussions with John Shaw in Delaware, and we did one paper on spin-to-charge conversion in topological insulator with the team of JP Wang. So my talk is about spin-orbit torque, but since there could be people in the audience who are not expert in spin-orbit torque, I will start pedagogically like many of the previous speakers. So spin-orbit torque is pretty much one of the most important topics in the so-called next generation spintronics. So if you remember, where Stefan was giving his tutorial yesterday, he told you spintronics started by looking at spin valves with parallel or anti-parallel magnetization. In the spin torque, you also use spin valves, which means this part here is normal metal, or use metallic tunnel junctions, magnetic tunnel junctions, in which case this is an insulating barrier, but you make two magnetizations non-collinear. So this is the key feature of any torque discussions. And if you have the standard device which has been around for at least 20 years, and it is also a prime example of why you need a theorist, because spin torque was predicted in mid-1990s when I was actually just starting the graduate school by Slonzewski and Berger, and then confirmed experimentally. So what happens in this device is that you inject a stream flux of electrons, standard unpolarized current. this ferromagnetic layer here is going to polarize the electrons in its own direction. This is why when the electrons come into the spacer, which again could be normal metal or insulating barrier, they're polarized in the direction of white magnetization in the left layer, polarizer. And then when they hit the next layer with the magnetization in this direction, quantum mechanics says only these guys can go through. So if only this component can go through, this means that this component, which is transfers, must be absorbed. Absorption of transverse component means somebody is depositing angular momentum into this second ferromagnetic layer with the black magnetization, and that something is going to cause that magnetization to perform dynamics. So from a viewpoint of quantum mechanics, everything should be solved quantum mechanically, and recently actually we did start developing a formalism when you can treat both electrons and these fixed black spins quantum mechanically, but let's say if you want to handle 10 spin 1/2s, you need 1 terabyte of RAM if you do it brute force. If you switch to TDD-MRG, time-dependent density matrix normalization group, then you might be able to handle 100 spins. But real magnets have millions of spins, which is why in experimental community, as well as in trying to treat realistic systems, you typically switch to so-called quantum classical formalisms. And here is one example that we also developed recently, when the magnetization dynamics is treated as a classical vector of fixed length. And then you use some quantum mechanical effects, but they are typically very important only at low temperatures. So in particular, this torque that comes from the absorption of this transverse component is going to induce a vector which can be decomposed in the standard magnetic tunnel junctions or spin valves into 2 vector components. So one component called damping-like torque is competing with damping, which is trying to bring magnetization back to its equilibrium position around some external magnetic field, while the other component of the torque called field-like is competing with the magnetic field which is trying to precess the magnetization. And of course the problem is as complicated eventually as any Newton's second law. For example, if I throw this pencil, which I'm not going to do because the pencil is very expensive, unless I tell you about the initial conditions and all the frictions in this room and stuff like that, you won't be able to tell me what the trajectory is going to be because you have to calculate this, and it could be chaotic and things like that. So in this case, you can get very complicated behavior. You have to solve the Landau-Lifshitz-Gilbert equation, and the complicated behavior lead directly to applications. So for example, if you succeed in doing something like this, magnetization starts from up, precesses, and eventually ends to down, this becomes a resource for memories, the so-called non-volatile magnetic random access memory. Here is an example of Everspin making this memory. Many Japanese companies are doing the same, this company in Belgium. So this will be this kind of application. You can get, under some other conditions between the forces and the frictions, you can get continuous precession of that magnetization driven by the current. In that case, that becomes a resource for a picot nanoscale microwave oscillator in gigahertz range, and this is this application here. You can even make elements of neural networks. So you can make a neural network based on the features of these spin torque devices, and there is a very beautiful article about the spin torque building blocks which you can download from Nature Materials, which summarizes these 7 applications of spin transfer torque. So the spin orbit torque is something that started in Grenoble in 2010, and essentially what happened in the spin orbit torque, you also try to pass a current and drive, as illustrated by this device from Tohoku University, current drives magnetization dynamics. But the key difference between spin orbit torque and spin transfer torque is that now you have only one ferromagnetic layer. And at first sight, this is very puzzling because if there is only one ferromagnetic layer which receives the torque, where is the other guy which is causing the spins to be polarized in a proper non-collinear direction? Well, that other guy which plays the role of a polarizing ferromagnet has to be a material with strong spin-orbit coupling effects, which brings this talk then into the realm of many of the discussions throughout the workshops. So in particular, in this case, they use tantalum to introduce strong spin-orbit coupling effects, either from the bulk or from the interface. Then people eventually switch to topological insulators in 2014 and later. And the latest fashion in this field, all these papers are just few months old in terms of publication. They came up maybe 6 months ago on the archive. The latest fad is to take the spin orbit coupled materials such as platinum as the standard one and attach it into a bilayer to a two-dimensional ferromagnet. So why would you be switching between these different choices? Why not get stuck with the so-called heavy metal ferromagnet bilayers? Well, for example, the team of Hyun So Yang in Singapore was able to perform magnetization switching, which remember is the key thing to get a non-volatile memory, with a current which is 2 orders of magnitude smaller current density than anything that has been done in the devices on the previous slide. So by switching to spin-orbit torque from spin transfer torque, you are saving a huge amount of joule heat that would be dissipated. And if you look at the energy wasted per switching cycle, it's only 60 femtojoules compared to 150 or even 4 picojoules that they have been doing with the spin transfer torque. In the case of 2D magnets, the temperature at which they operate is not still room temperatures you need for real applications, and the current density is much larger, but this structure is not the ultimate limit. In the paper, for example, they tell you this is the first step toward the ultimate limit. What is the ultimate limit? Well, the ultimate limit is not few nanometers thick FGETE and few nanometers thick platinum. The ultimate limit is what is the topic of this workshop largely, is a van der Waals heterostructure in which you have, for example, one monolayer of a 2D ferromagnet, one monolayer of something spin orbit, maybe one monolayer of something insulating conducting, and you try to do spin orbit torque on that. At the moment, I am not aware of any experimental group which has achieved this, but since I'm a theorist and I have big supercomputers, which you have seen in the slides of Stefan Roche, I can design these things in the computer. And this is what this talk is about. We are kind of going ahead of what experimentalists are doing and also trying to make very precise predictions because we use in this whole business the so-called first principles quantum transport, which means no free parameters. We consider real materials and we try to tell you what would happen if you pass a current into bilayers of 2D ferromagnets and something spin orbit. By the way, the spin orbit torque would also have application for those memories with ultra-low dissipation, but here is another paper, extremely beautiful, in which Hideo Ono, just before he became president of Tohoku University, with his team, was able to create a 4x4 neural networks based on the nonlinear characteristics of anomalous Hall voltage that is eventually generated, because in the spin orbit torque, once the magnetization starts doing these dynamics, you're going to pick up the voltage between these two contacts, and that anomalous Hall voltage would be changing in this hysteretic nonlinear fashion, and that becomes a resource to create one neuron. And if you take 16 of these elements, as they did it in this paper, you have a full neural network based on spin orbit torque. So why the theorists have to jump in this field? Because experimentalists could be cycling through the materials by themselves. Well, it turns out, for example, that the team of Dan Ralph did this seminal experiment on ferromagnet topological insulator heterostructures, but very quickly they gave up on this system. And one of the reasons why they gave up is that they were relying on these simplistic pictures, such as that if you have a topological insulator, then before you cover it with a ferromagnet, you have this Dirac cone with spin momentum locking of these massless Dirac fermions. Then they say, or not they, but theorists tell them, look, if you put a ferromagnet, the only thing which happens, you open a gap. And they said, wow, this is so bad, because most of the current will go into the permalloy, all the interesting stuff is the interface, but this brown guy is very resistive. Most of the current goes into permalloy. This is what is written here in this red ink, which is excerpt from their Nature paper. And since most of the current is wasted by going into the blue guy without ever sensing the interface with spin orbit coupling, that means this torque is going to be very inefficient. Therefore, don't do it. And for many years, there was no progress in this field. I actually organized the first workshop in 2015 in Grenoble on this topic, and people were saying, let's give up, because this is a very inefficient device. We are never going to switch the magnetization at room temperature. Nevertheless, as I showed you, the switching was achieved in 2017, and there is actually a misconception about all this stuff, because as you're going to see, all of this stuff is actually wrong. You need to go into realistic physics and understand what happens when you bring two materials into contact and what kind of states you have at the interface. So one way to know the states of the interface is to shine ARPES photons onto the surface of, let's say, material in contact with vacuum, and then you see what theorists have calculated at the time as the Dirac cone on the surface of topological insulator, and then experimentalists shine ARPES beam onto the same surface, and they confirm that you see this Dirac cone. But unfortunately, if you cover now topological insulator with a ferromagnet, which is what you need to do the spin orbit torque business, then ARPES is not going to penetrate through, let's say, more than 1 or 2 nanometers of cobalt in this case. And so nobody can tell you what is the state at the interface between two materials, but nevertheless, if you know how to calculate this, combining DFT with something else, because plain DFT doesn't immediately lead to these spectral functions you watch in ARPES, then you can actually put a plane anywhere you want, and I can tell you from the calculations what is the state going to be. Once I see the state, I can examine it with my own eyes or with some data science, but in this case it's a human operator which has to examine, and I can kind of guess what would happen if I pass a current through these planes. If the plane has a non-trivial spin textures, once I bring it out of equilibrium by passing the current in this direction, I'm going to get non-equilibrium spin densities. And this is the key to eventually produce spin torque. So this is the idea of this whole talk. Let's look at these spectral functions at any plane of any heterostructure with the kind of standardized machinery we developed. Once we see interesting heterostructures with non-trivial spin textures, then let's push them out of equilibrium and check if they're going to produce useful torque for these operations. So there was a lot of discussions throughout the workshop of this basic stuff, and I have 2 slides on the crash course on spin orbit coupling and Rajva spin orbit coupling. One could ask why again repeat something that other people have been discussing. Spin orbit coupling is magnetic field in reference frame of electron. Well, the reason to repeat is Feynman, because if you read his lectures on physics, he tells you everything you know in theoretical physics, you have to be able to derive in at least 10 different ways. I'm not Feynman. I cannot do what he was doing. By the way, he was a great friend of Brazil. This is what he was doing when he was visiting Brazil. So in the afternoon, instead of sitting in this kind of room and giving lectures, he was going on the beach and learning how to play different types of these percussion instruments. So we have to do the conference. So in any case, if you follow Feynman and I tell you how you should understand spin orbit coupling in a kind of more intuitive way, the idea is that you can discuss spin orbit coupling in the frame of electron, but unfortunately, you are not doing your experiments in the frame of electron. So it is actually better to go into the laboratory frame. If you go in the laboratory frame, this is what you see. Electron in its own rest frame has a non-zero magnetic dipole moment, and it has 0 electric dipole moment, but then specialty relativity tells you that this mu and p vector are going to be transformed in the limit of v square over c square much less than 1 into the same magnetic dipole moment. You don't see this 1 over 1 square root of 1 minus v square over c square because of this condition here, and there will be a new electric dipole moment in the frame of laboratory electric field. And then the spin orbit coupling is nothing else than the p dot e term that most of us have seen in some kind of high school education. The only thing you cannot pull from your high school education is factor 1/2. So factor 1/2 either has to come from expanding the Dirac equation, or you have to know that in specialty relativity, any accelerated system also has something called Thomas precession, and that factor 1/2 compensates for Thomas precession. Once you quantize this classical expression, P dot E, potential energy of a dipole in the electric field E, then you get exactly the same spin orbit term that would take forever to derive from Dirac equation while obeying gauge invariance. For example, there is a paper by one of these spin orbit experts who sampled 15 books on quantum field theory, and he says everyone has a wrong derivation of spin orbit coupling, that term over there, as well as Darwin term and stuff like that, because of disobeying gauge invariance, which is always like the great hurdle for theorists. So again, the value of this picture is that if you look at V cross mu, you can take your right hand and immediately see how this dipole forms and how the force is going to act. For example, if I start with spin up, that means magnetic dipole moment down because electron has negative charge. V cross mu means dipole moment to the left. The dipole moment comes into the target with a non-zero gradient of electric field, and then you get separation of spin left-right because of, again, force that you can pull out from classical physics. So this becomes the explanation in a hand-waving fashion of what is called extrinsic spin Hall effect, because in this case impurity separates spin up and spin down in the transverse direction, and that means you're going to get spin current in the transverse direction in response to injected longitudinal current. So the crash course on Rajva spin orbit coupling says now you take a Rajva spin orbit coupling, which is also some kind of sigma dot p term, like a Zeeman term, but with a p-dependent magnetic field. In one dimension, that gives you just two parabolas if Rashba is 0, which is spin degenerate. If you have real Zeeman term, you split parabolas vertically so that you have a non-zero spin density even equilibrium. In the case of spin-orbit coupling, because you have p-dependent magnetic field and also you are forbidden by the time reversal symmetry to have non-zero spin accumulation, the splitting of parabola has to be horizontal. You take these two parabolas and go into a realistic 2D system, you rotate them around the z-axis, and that's how you get this famous Rashba energy momentum dispersion. In graphene, you get the same thing discussed in many slides, but you are splitting Dirac cone. If you send one of these Dirac cones to infinity, you get topological insulator. So topological insulator is a direct cousin of a Rashba spin-orbit coupling without going into any kind of topological discussion, because it looks like somebody took one of these two Dirac cones and sent to infinity and then brought it, for example, back to the bottom of the cube of topological material. Both Rashba systems and topological insulators do have the spin momentum locking, which in this case is easy to understand. Most of the pictures I'm going to show in a moment are not going to be easy to understand because you don't have just some kind of simple two circles you have in the case of Rashba. And spin momentum locking simply means this. If you tell me that momentum is this, I tell you spin has to be down. If you tell me momentum is this, I tell you spin has to be to the left. If you now look at this simple spin momentum locking texture in the case of Rashba spin-orbit coupling or one circle for topological insulator, you can immediately guess that if I pass a current in this direction, I'm going to create imbalance between right k vectors and left k vectors, and that is going to generate non-equilibrium spin density in response to current flowing along the x-axis. The spin density will be in the transfer direction along the y-axis. So this kind of generation of spin densities in response to current or electric field is forbidden in equilibrium, because in equilibrium under time reversal Ex goes into Ex, Sy goes into minus Sy, so this has to be 0 equals to 0. But out of equilibrium, you break time reversal invariance, and then you have ability to generate non-equilibrium spin in the transverse direction due to current flowing along the longitudinal direction. So what is then the difference between topological insulator texture and spin momentum locking textures of Rashba type? Well, it turns out that the strength of this Sy you generate in response to electric field in the case of Rashba spin orbit coupling is cut by this factor which is much less than 1. If you get rid of the second Fermi circle, this guy disappears, and it looks like as if you have increased this by several orders of magnitude. So essentially, topological insulator from the viewpoint of spintronics acts like a Rashba 2-dig on steroids, because you get rid of the second circle, and the second circle reduces the compensation of this non-equilibrium spin density in response to current. So now, armed with these two crash courses that I kind of briefly overviewed, and they were overviewed also yesterday, so you probably have some feeling for this, let's take a look at cobalt. So this is the surface of a cobalt with a spectral function calculated combining density function theory and green functions. So it is exactly the same object that people would scan in ARPES. If they have spin ARPES, they can also cut this 3D spectral function you should imagine being rotated around the z-axis. And if you cut it along these dashed white lines, you're going to get a cut, which is a Fermi energy plane of the spin textures of the spectral function. And then you plot the spin texture, and you see exactly the Rashba spin texture. You see red and white arrows circulating along the circle. So in other words, even though cobalt by itself does not have spin orbit coupling of this type, of Rashba type, once you cut it into half, you have created inversion asymmetric system, and now surface of cobalt becomes a Rashba system. Typically, Rashba systems in 1990s or going back to the 60s were studying in semiconductor heterostructures. These days, these systems are actually more important because you can get much bigger Rashba splitting. So here is example. The simplest example, surface of cobalt in contact with vacuum has a Rashba spin orbit texture computed by DFT we just saw in a simplistic fashion discussed on the previous slide. Now we cover surface of cobalt with topological insulator, and the spectral function changes dramatically. Again, this is the spectral function you would not be able to see with ARPES because it's buried inside the whole heterostructure, but I can go with a computer and calculate it. If I look at the spectral function, spin texture cutting the spectral function, I do see it's a completely different one, and about 0.35 eV below the Fermi level, I even see the topological spin momentum locking. So in other words, cobalt has become topological, and this is the meaning of topological spintronic, operating with this kind of textures, not at the Fermi level, but at minus 35 eV below the Fermi level. You could ask what would happen with other materials. Well, this is example cobalt MOS2, cobalt WSE2. By analyzing these spin textures, you could guess what kind of current density, what kind of non-equilibrium spin density will be generated in response to current, but they're much more complicated, and there is no way to say, aha, I pass the current this way, and I'm going to get non-equilibrium spin density that way. So this is why you need very microscopic calculations, because there is no way to guess, like in the case of Rajba. Aha, I have two circles, I pass the current this way, the spin density has to be the other way. By the way, you could also ask what would happen if you look on the topological insulator side of topological insulator cobalt heterostructure. So just to warm up, I'm showing the same spectral function from that nature physics when the topological insulator is in contact with vacuum. As soon as you start adding 1 monolayer of cobalt, 2 monolayers of cobalt, 3 monolayers of cobalt, Dirac cone is pushed by charge transfer into the valence band, and then it gets hybridized there. So there is nothing simple like Dirac cone anymore. There is no simple spin momentum locking. In fact, any attempt to write some kind of simplistic model based on your physical intuition fails. These guys try to write some kind of model based on Fano resonances, what would happen if you couple metal to the surface of topological insulator, and whatever they came up with is very far away from reality that we get from these first principles calculations. So what is now the non-equilibrium thing, which is really what I'm doing? I'm just preparing myself to prepare a Hamiltonian using this knowledge from the previous few slides and shuffle through quantum transport formalism. Well, in order to be able to treat devices in arbitrary geometry, arbitrary number of layers, and so on, and these heterostructures, we use the non-equilibrium green function formalism in the Landau setup with 2 macroscopic reservoirs taking care of dissipation. One green function gives me the retarded one, which you have probably seen in many courses. It gives me density of available quantum states. If I'm in equilibrium, the states which are defined by the retarded green functions are going to be populated according to Boltzmann and Gibbs using Fermi distribution function. And that's how I can construct equilibrium density matrix. But once I'm out of equilibrium, this fails. And I need a new green function, which is going to tell me how states get populated. When we teach students quantum mechanics, we usually tell them you connect whatever you calculate to the real world by computing this kind of expectation values. But this is good for textbook, getting the degree, PhD, or solving homework problems, but not good for research. Because this kind of quantum mechanics doesn't know about temperature, doesn't know about non-equilibrium boundary conditions, so you have to switch to something else, which is quantum statistical mechanics. So in all of this business that we are doing, we are essentially calculating trace of some density matrix times some operator. If we have a time-dependent problem, nowadays in the past 2-3 years, we can even calculate time-dependent density matrix, 0.1 femtosecond by femtosecond. But in this talk, I'm mostly going to do the steady-state density matrix, non-equilibrium one, in the presence of steady-state current. And in that case, I'm calculating this guy, integral of this G lesser dE. Since in quantum mechanics, anything you want to calculate is a trace of some operator, which operator should I stick in to get the torque? Well, if I start from a Kohn-Sham Hamiltonian of the non-collinear density function theory, and I define the torque operator as the derivative of the spin operator, then the torque operator is going to go into the slot of a trace with a non-equilibrium density matrix, and torque at the end of the day is fundamentally this expression here. So what this expression says, you can take anything, you can take your cell phone, sponge, or real magnetic material. You have to take a cube of whatever you're considering, you have to take a point of space R, and you have to check, is there a non-zero cross product of this exchange correlation magnetic field, which comes from intrinsic magnetism of your material, and non-equilibrium spin density. If that cross product is 0, you will get a local torque at that point in space. If you want to get a torque on the whole ferromagnetic layer, for example, you just have to integrate this expression. If there is a magnetic proximity effect, which means non-zero magnetic moments formed in bismuth selenium or graphene or whatever, you would extend your integration even in that layer of proximity effect. So the bottom line is that this explains why you actually don't even have to know microscopic mechanisms, or why that argument that current flows into permalloy and doesn't sense the interface is wrong, because in that experiment of Dan Ralph, the only thing which matters is there a spin-orbit coupling here on the permalloy side, and if that spin-orbit coupling is there, that will generate non-zero spin, non-equilibrium spin density, that would give you non-zero cross product, and then you have a torque. So in other words, from the viewpoint of what you really calculate, as opposed to providing physical pictures and stuff like that, you really have to calculate non-equilibrium spin density. That non-equilibrium spin density can come from a spin Hall effect, as was illustrated in one of these previous slides. It can come from interfacial effects, Rashba-Ellerstein effect, but that's what you need to do, to find out what the non-equilibrium spin density is independently of the microscopic mechanism. Here is an example of passing current through topological insulator, and then on the surface you get these textures which actually look exactly like Rashba stuff. You have one non-equilibrium spin density on the top surface, you have another one on the bottom surface, but since there are evanescent wave functions penetrating from the metallic surfaces into the bulk, there is actually a conducting layer of a thickness of 2 nanometers, which also has non-equilibrium spin textures. And they are much more complicated and nothing like this Rashba-Ellerstein effect or inverse spin galvanic effect, just transfer spin density. So this is all the stuff which comes by plugging in straight DFT Hamiltonian. So pay attention here, I'm not doing any tight binding derivations fitting. I straight take a DFT Hamiltonian in local orbital representation, and orbitals are non-orthogonal. There are many more orbitals, typically 100 per atom, as opposed to what you do in tight binding with 1, 2, or 3, and that gives you access to directly to first principles band structures, all these interfacial states that I've shown you, and then you shuffle that through this green function formalism, and that gives you access to currents, non-equilibrium spin density, and so on. Of course, in this case, I'm calculating this kind of quantity. I take S expectation value, which is h bar half trace of non-equilibrium density matrix times the Pauli matrix. So this is how we get the non-equilibrium spin density pictures in this slide, as long as we know to calculate this guy here. Of course, Pauli matrix is trivially stuck in. So now comes the apex of this talk. Let's try to replace everything with 2D materials and switch to this van der Waals heterostructure. So there is a very nice review article. There is actually 6 of them, so you don't even have to read the original papers anymore. There is a community of people who write these review articles for you and cut short all the knowledge you have to have. So in this review article by Morpurgo and Novoselov, they tell you, look, there's all these different 2D materials. They're very strange because they can have magnetic orderings that you never see in the bulk. In particular, the one of great interest for us in this talk is chromium iodide 3, which has in bilayer form one layer with magnetic moments up and the other layer with magnetic moments down. So it is an antiferromagnet composed of 2 monolayer ferromagnets. There is, of course, a story from the courses in statistical physics you took when you were very young, that you cannot have magnetic ordering in 2 dimensions because thermal fluctuations are going to destroy anything except this Kostelis-Thouless transition. In 3 dimensions, any kind of freedom to rotate in any direction for Heisenberg model leads to zero magnetization. But of course, these are real systems which are layered. Even if you go to only one layer, there's going to be a huge uniaxial anisotropy due to spin-orbit coupling. And that makes, for example, the CRI3 monolayer act more like an Ising model. An Ising model, of course, as we know, does have a non-zero transition at a finite temperature. So here you can actually see what is the critical temperature of these monolayers. Monolayer would be here, as you thin the van der Waals ferromagnet by normalizing to the 1 here means the temperature of the bulk material. So one of the most interesting discoveries from a practical spintronics viewpoint in this field has been, let's take the CRI3, expose it to electric field and switch it from antiferromagnet to ferromagnet, which means both layers in this case pointing in the same direction. Unfortunately, this is a very good setup in terms of reducing Joule heat, but it is bad because they apply magnetic field in this direction. And so with magnetic field, you lose ability to integrate this into devices because there is no way to generate magnetic field on nanoscale. Most of the spintronics in the past 10, 15 years has been all electrical spintronics. You don't want to deal with external magnetic fields. So this is why we came up with this design. Let's take the bilayer of chromium iodide. Let's put tantalum, selenium underneath, and let's pass a current in this lateral direction. So this is like a really minimum, only 3 layers spin orbit operated torque device. This chromium iodide is not conducting, it's an insulator, but this guy is metallic. It was also discussed in the talk of Iris Ferreira. And since it is a metallic, in quantum mechanics, any metallic wave function wants to penetrate as much as it can, it is going to inject evanescent states into the first layer of chromium iodide. So these evanescent states, once you pass a current, are going to conduct. And here you see non-equilibrium spin density on the first monolayer, which is this guy here of chromium iodide, but nothing shows up on the second. So this is a good news because that means that this non-equilibrium spin density, the green one here, SCD, cross product with M1 is going to give you torque. If the torque is good enough, it might switch M1 from down along the z-axis to up along z-axis, and that is eventually going to produce a ferromagnet out of antiferromagnets. I'm going to introduce essentially non-equilibrium phase transition driven by spin-orbit torque. The spin-orbit torque, by the way, is usually discussed in this context as a feel-like, damping-like, but in reality, it is much more complicated and very few people are able to calculate or even measure the full angular dependence. For example, we have developed this methodology. Kirill Belashenko has another one. So we can actually calculate torque at few points on the unit sphere and then pass this infinite series curve through these points and decide which of these terms are non-zero. So for example, there is 4 of these terms which are non-zero and 2 of these which are non-negligible, and that becomes a function that then gives me an analytical expression for my spin-orbit torque. Only first of these terms is actually feel-like torque. The other one is a mixture between feel-like and damping-like torques. So now I combine this in some kind of multi-scale self-consistent fashion with Landau-Lishos Gilbert equation, and what I see is that if I apply a DC current, eventually I'm going to switch magnetization to some kind of strange direction here. But if I start applying pulses of current, the magnetization is just going to go between -1 and 1. And that's exactly what I want, because if I flip from -1 to 1, M1 along the z-axis, I will get non-equilibrium phase transition from the antiferromagnet to ferromagnet. And here is the movie. Let's pray to Microsoft that it's going to work. So here it is. Nothing happens. Pay attention to the red line because I'm going into the region of the pulse. I'm now going to hit the current pulse. M1 starts precessing as I try to describe hand-wavingly, but picture is much better. It goes very quickly to the positive side of the z direction. M2 is doing some small oscillations because it's exchange coupled to N1, but this is the final state. And the final state is a stable ferromagnet up to the spin wave precession until the second pulse is being hit. Now is the second pulse puts it back. So the state is stable. I can very controllably switch between antiferromagnet, ferromagnet, then back to antiferromagnet. How can I use this in spintronic applications? Where one option would be to take this heterostructure and apply a read current in the vertical direction, in which case this becomes a magnetic tunnel junction kind of device, and I see that I'm generating 66% tunneling magnetoresistance as I'm shifting from ferromagnetic to antiferromagnetic phase. Another way would be just to look at the anomalous Hall voltage on the lateral contacts, so somebody would have to build a contact. I'm a theorist, of course, I not build contacts, but experimentalists would put a contact on this side and this side, put a voltmeter somewhere here, and they would see change in voltage as the magnetization performs the dynamics due to the change in anomalous Hall effect. So there is another system. Okay, I'm running out of time and I'm actually running out of slides, which is a good news. So here is another system, which is actually very important because of the fact that you can decipher many things. So for people who work in spin-orbit torque, the biggest mystery is the following one, and I will say it very slowly. So the biggest mystery is where is the anti-damping torque coming from? Because that's the one which does the switching, even though in the previous slide I was switching with a kind of feel-like torque. So the anti-damping torque is typically considered to be the result of spin-Hall effect. You pass a current this way, and you have some kind of spin-Hall current going that way. But all of this 2D van der Waals heterostructure we're building right now do not have any spin-Hall effect because there is no bulk. So they're a beautiful setup to examine anti-damping torque due to interfacial spin-orbit coupling in the absence of spin-Hall effect. And that's why pretty much we set up this device. It has CGTE, it has graphene, it has WS2. What happens here is that WS2, as in many previous talks, introduces spin-orbit coupling in graphene, while CGTE introduced magnetic ordering in graphene. So this becomes doubly proximity as graphene. Graphene, which is neither magnetic nor spin orbit in isolated form, is here both ferromagnet as well as spin orbit material. So then we apply a current and we see only feel-like torque, if you want, for experts. And that means with the interfaces only, in a completely clean ballistic system, there is no anti-damping torque. But when you apply a gate voltage to introduce a potential barrier in this system and reflect electrons, and that seems to be a key concept that is required to get this interfacially driven anti-damping torques, and immediately we get the red curve, which is anti-damping torque due to application of gate voltage, which we do not have a possibility to play with in the case of bulk three-dimensional ferromagnets. And moreover, if you see the number, I can change this torque by 2 orders of magnitude simply by playing with this gate voltage, or Fermi energy in this case. So I fix the gate voltage and I use another gate to change the Fermi energy of graphene, and I'm modulating torque in a way that has never been demonstrated with any conventional three-dimensional ferromagnet. So there is this one slide which I'm going to skip about what would happen if you would cobalt in contact with TMDs. And again, I apologize for taking a little bit extra time, but this is my conclusion in pictures.
Okay, thank you, Branislav, for a really nice talk. I think that we have time for one question. So is there...
Or maybe we should have like a 1 hour discussion between 4 and 5 in general, so we don't have to rush with